Good evening, everyone, and welcome back to AISC Night School. This is Stability Design of Steel Structures, Applying Modern Methods of Structural Analysis, presented by Donald W. White and Ronald D. Zimian in conjunction with SSRC, the Structural Stability Research Council. Today is March 9th, 2015, and this is Session 6, Stability Design of Low and Medium-Rise Steel Buildings. I am Brett Liu. I am with AISC, and I'll be moderating today's presentation. I'd like to get started on tonight's lecture. Please welcome back tonight's speaker, Dr. Donald White. Donald White is professor at the Georgia Institute of Technology. Dr. White's research covers a broad area of design and behavior of steel and composite steel concrete structures, as well as computational mechanics, methods of nonlinear analysis, and applications to design. Dr. White is a member of AISC's Committee on Specifications, as well as SSRC, the Structural Stability Research Council, where he has been the past chair of Task Committee 29 on inelastic analysis and Task Committee 5 on beams. Dr. White has received many awards throughout his career, including the 2005 Special Achievement Award from AISC. He also received the 2006 Shortridge Hardesty Award from ASCE. In 2009, AISC awarded him with the T.R. Higgins Lectureship Award, and in 2010, he received the Raymond C. Reese Prize from ASCE for his research and development activities in the area of stability analysis and design. With that, I want to welcome back Dr. White. Thanks for being here, Don, and I'm going to hand things over to you.
Okay, and welcome back, everybody. We've got a number of things that I hope you'll find useful tonight. See if I can get this rolling. We're going to focus on low and medium-rise steel buildings, and I think some useful techniques with that in mind. The order of the presentation, I'd like to first kind of give an overview of an example building we're going to be focusing on to look at the work. We'll then move into looking at design of the brace frames for that building. Big focus is how do we estimate the side sway amplifier, B2, given wind drift limits, seismic drift limits, seismic P delta limits. We'll also talk about how we can use a fairly cool way of handling the live load reduction considerations, where we put those into the analysis and what the advantages are for that. Then the third topic, we'll move into looking at the design of the moment frames in this building. We'll look at how we can back out a first order wind drift limit, considering second order effects and why we might want to do that. We'll talk kind of more generally about characteristics of upper bound side sway amplifiers, B2, some back of the envelope preliminary strength design. A lot of the emphasis tonight is actually on kind of preliminary design type calculations. And we'll wrap up with story stiffness design. So let's get rolling. The building we're going to talk about is what I call the Cirque du Soleil building. That's because I put it on a lot that's right next to Atlantic Station. If you've been to Atlanta, and the Cirque du Soleil Circus usually comes there every year, so I couldn't figure out a better name than that to use for the building. We're going to be using the ISC 360 standard, ASCE 7 load standard, IBC 2012. The structure we're going to look at would classify as low-rise, rigid, regular-shaped, simple diaphragm. It's an enclosed building, risk category 2. So the importance factors for snow and earthquake 1.0. Again, the building's located here in Atlanta, theoretically. The wind exposure, let's assume exposure B. No topographic effects. We're going to use the directional procedure or building of all heights methods in terms of pulling in the loads that we'll use for wind. Given the site, basically assuming a site class category B, we end up with these spectral acceleration values that you see here. That pushes us into seismic design category B in ASCE 7. And we're going to look at designing this building as a system not specifically detailed for seismic resistance. So our R factor, omega factor, and C sub D factor are all 3. The diaphragms in the building here would classify as rigid. Notice that's in red here. There's a couple of slides as we move through, or more than just a couple, a few slides as we move through where I made some last minute changes. Most of them are little piddly things like this, but just to make it a little more clear, I think there's a couple of typos that I'll point out. But anything that's not in the slides you have will show up in red, like you see here on the bottom. And I understand from Brent that he'll make the hard copies of those slides available, or the PDF of those slides available to everyone after tonight's lecture. Okay, here's the basic floor plan, nice box. The building actually comes from Luke Eschwender's textbook that's referenced back at the back of the slides that you have. Lou's also used this, I believe, in a number of different presentations. We have moment frames on 2 exterior walls, basically on the east-west, taking lateral load in the east-west direction. We have brace frames on the exterior walls, column lines 1 and 8, to take loads in the north-south direction. So here's a more orthographic view of all the frames here in the building, our lateral load resisting systems. This is pretty much all we're relying on for lateral load resistant systems here in this particular example building. Here's an elevation view of each of the moment frames, basically both being the same. The top story is 14.5 feet to accommodate roof slope down to roof drains on the interior up at the roof. We'll have a column splice at the 3rd story level. If we look at the brace frames, same deal. Brace frames there are on between column lines C and D, and again, change in the column section at the 3rd story level. So here's kind of the overall building with all the framing, both lateral systems as well as gravity load systems shown here in this particular view. If we move on to look at some floor plans, actually here's the roof plan showing live loads on the roof. We've got a mechanical area that's shaded in gray there in the middle of the building, and other than that, basically we've got a 20 pounds per square foot uniform live load that would govern in terms of comparing that to the other roof live loads. But we're going to focus on the main earthquake load combination number 5 in some of the calculations, and so we're going to use the uniform snow plus rain on snow load of 8.5 PSF when we look at building everything for that load combination. We could have some snow drift loads that could control some things locally on the roof, but in terms of overall effect on our lateral load resisting frames, we're pretty much dominated, would be dominated by these cases you see here. And moving into the floor plans, basically we're taking an 80 pounds per square foot in office area that's in the white areas here of the floor plan. In the middle of the building, we're going to use 125 pounds per square foot non-reducible live load. That was with an intent of maybe that's storage, files, things of that sort in that area. 100 pounds per square foot non-reducible there toward the ends of the building between column lines 1 and 2 and 7 and 8 at the bay containing stair openings. Second floor plan, pretty much the same, except we have an atrium there between column lines 4 and 5 and A and C. And then other particulars here about this simple example, nice rectangular building. We're going to assume the slab overhangs are 6 inches outside the outer column lines and at slab openings. The building envelope itself is 9.5 inches outside the edge of the slab. The building has 2-foot-high parapets at the roof, parapets being a continuation of the exterior facade panels above the top of the roof deck. Around the mechanical area, at the roof, we've got 6-foot-high screen walls that'll basically the same type elements as what we're using for the facade. Total height of the facade panels supported at the roof we're taking is 9.25 feet. Total height of facade panels on all the other floors, 13.5 feet. So the facade panels aren't quite centered on each floor level. In terms of the vertical weight that's supported, it gives us 7.25 feet that would be supported at the foundation level. And then in terms of working through the calculations, just to keep things simple, we're not going to consider any openings for stairs, etc. We'll base the load combination calculations on idealized solid diaphragm, no openings at all the levels. The facade, basically, let's assume we've got architectural precast concrete panels, spandrel supported. Dead weight of those panels, 30 pounds per square foot on the wall area. So kind of something like you see here in the photo, essentially say a ribbon window system and the precast wall panels in there as well. Let's talk about the dead loads we'll assume for doing our calculations. So at the roof level, the structural dead load, 20 pounds per square foot. Uniform dead load allowance, 2 pounds per square foot column allowance there at the roof level, here at the roof level, except in the mechanical area, bumping it up to 22 pounds per square foot uniform dead load and 2.5 PSF for columns in the mechanical area. The mechanical area, let's assume that we've got 60 pounds per square foot allowance for equipment. And I'm going to take that as being something where I know that's my equipment weight fairly well, so I'm going to treat that as dead load in the calculations here. Moving to the floors, typical concrete and slab and metal deck, 60 pounds per square foot, 8 pounds per square foot allowance for all the structural steel framing within the floors, 12 PSF for miscellaneous ceiling, mechanical, electrical, plumbing, etc. So that gives us 80 pounds per square foot total for dead load. Again, 2.5 pounds per square foot we'll take as an allowance dead load for columns. Looking at wind load pressures from the directional method or building of all heights method for wind load to the east. Turns out for a nice box like this with lateral load resisting systems all on the exterior walls, we don't have to look at any ASE 7 load combinations other than what ASE 7 calls case 1, which is uniform wind in each of the principal directions of the building here. So east wind gives us on the windward wall, the wall closest to us here, the different pressures that I'm showing you labeled on those areas in PSF. And then on the leeward wall, 24.2 on the parapet, 2.7 suction on that wall. And then I'm also showing you the screen wall load here. Now, of course, given that we're idealizing this building as having rigid diaphragms, in the plane of each of the diaphragms, those diaphragms basically we're taking these loads from our wall systems are distributed out to our lateral load frames on the exterior here, our column lines A and F. North-south, so looking at the wind load case in the north, pretty much same pressures on the windward wall, slightly different pressures on the leeward wall by the ASE 7 calculations. Pretty much same loads in terms of the wind loads on the parapets and screen wall. So same deal again in terms of distribution of those lateral loads. The diaphragms basically working as simple diaphragms or simple span beams, taking the loads out to the lateral load resisting systems. In terms of seismic load, we'll take the effective seismic weight based on ASCE 7 as the dead load, plus 25% of the live load in the storage areas there in the middle of the building. I'm taking the operating weight of the permanent equipment, a bit high, but 60 PSF, pretty much the equipment load that we went with there for the mechanical area at the roof. And then ASCE 7 indicates that we have to take a 10 PSF minimum partition allowance, or higher than that if your partitions are actually larger than that. We're going to take the 10 PSF partition allowance in the areas where the live load is less than or equal to 80 PSF, so basically the main office areas of the building. So if we total all that up, doing our dead load or weight, seismic weight takedowns, we end up with a seismic weight of the roof, at the roof of 959 kips. We end up with a seismic weight at each of the floors, 2574 kips, neglecting all the floor openings. Then we, if we look at that to get our total seismic weight for the building, it totals up to 8,680 kips. Moving on to basically summarizing what we would work from, not focusing on all these calculations, but focusing more on the stability design calculations here. Our building periods and seismic coefficients, north-south, are going to assume that basically our building periods within the plateau of the response spectrum, and so 0.682 seconds we're going to take as our building period based on estimate for brace frame. It gives us C sub S of 0.05. East-west on our moment frames. A frame like this, a lot of times the moment frames are going to be flexible enough so that we may have a period pushing out close to the maximum allowed period that ASCE 7 will let us use for our seismic calcs. So I'm going to go with that, and that's 1.175 seconds. Now, of course, our period estimate can often be a critical thing in terms of refining and getting the loads that we actually want to design for or need to design the building for. Other things, building site class could be an important thing here. We basically assumed site class, or I assumed site class category B in coming up with the seismic loads. If we're not happy with the seismic loads and we want to look at reducing the mass of the structure, if we need to, we could design the frame as an ordinary steel moment frame or other seismic designs to try to get the seismic forces down. But what we've got here, we're going to pretty much go with the design as I indicated earlier, where we're assuming that the building does not have any special detailing for seismic design. So going with that, if we basically look at totaling our wind and seismic north-south loads at each of the levels of the building, you have what you see here in this slide. We don't have to look at any wind eccentricity effect on this building. If you could look at it, but you'd basically be able to convince yourself that the uniform wind without any eccentricity effect is going to govern. The seismic eccentricity, though, we need to look at. And so I'm showing you the 0.05 of the 210-foot width here of our structural system in the building. So 10.5 feet is an accidental seismic eccentricity. And I'm going to assume that my brace frames, they're spaced that 210 foot apart, relatively far apart compared to the moment frames. Also, the brace frames tend to be stiffer in terms of lateral systems. So I'm just going to assume for purposes of calculation that this seismic eccentricity effect gets picked up entirely by just the braced frames for my preliminary design. All right, so doing that, then we would end up with the roof, fourth level, third level, and second level wind and earthquake loads that you see here, and then so giving us a total base shear 147.2 for the wind loading and 240.2 for the earthquake loading. Now for the characteristics I've given to you from this frame, ASCE 7 would also require that we include a vertical seismic load effect in the earthquake load combination of 0.2 SDS, which is 0.03. And of course the common practice for that is to build that into the dead load factor. So we'll use a 1.23 factor for the earthquake load combination dead load rather than 1.2. Same sort of deal in the east-west direction, but again, assuming that the brace frames are relatively stiff and further apart than the moment frames, I'm not including any handling of the torsional load from the accidental seismic eccentricity on the moment frames. I'm assuming my brace frames are taking all that here to rough things out. And so here's what we've got for our moment frames then in this case. So total base shear from wind in the east-west direction, 72.7, and a total base shear from the earthquake, 126.9. And I believe those are loads per frame. All right, so as I've mentioned before, we're going to target the ASCE 7 load combination 5 to work on various example calculations here. Emphasis on looking at some of the stability design considerations. If we look at the various load combinations, this earthquake load combination tends to dominate for a large number of the frame members in our lateral load resisting systems. So it's reasonably representative to kind of, we're going to focus on the bottom story, and so definitely the bottom story, this load combination is tending to dominate the design. In terms of the braced frame design, we're going to use the effective length method for the brace frame design. So that basically means that we're going to use a nominal stiffness in terms of doing the analysis calculations for the brace frames. The direct analysis method would include a stiffness reduction, and it could be argued that that stiffness reduction actually is appropriate and gives a better estimate of the true internal forces. In other words, we get a little bit of a stiffness reduction as we approach ultimate strength levels, and therefore we have a little larger amplification of the lateral load effects on the brace frames as well. But we don't really gain any advantage for that, and the differences tend to be rather small. And so we're going to just go with the effective length method for brace frame design here. When we go to the moment frames, we'll use the direct analysis method for the moment frames, and so I'll highlight where the direct analysis method calculations come in for that. Now, an important thing to keep in mind, which I know many of you as practicing engineers probably know very well, in many cases the member selections for the brace frames in a building like this are going to be largely governed by strength, whereas the member selections in the sway moment frames, at least a decent fraction of the members that we're going to size in our sway moment frames often will be governed by lateral stiffness. Okay, so I think we'll go a little bit further and kind of get into the calculations a little bit, Brent, and then we'll stop here in just a little bit to check if there's any questions. So let's work on the brace frames here. And the order of the presentation, we're going to do some basic vertical load takedowns to get oriented to everything. Then we'll focus on upper bound estimation of the side sway amplifier, B2. And I think once we get to that point, then it'll be maybe a good place to stop for any questions. After that, we'll look at some live load reduction considerations that can have some impact on our second order effects in the structure. And then we'll wrap up with designing the bottom story column of our brace frame. and our bracing diagonal and our brace frames for our load that you see is coming here from Appendix 8. Similar to the previous lectures, the equations over here in the right side of the screen are basically the references to equations numbers in the specification. All right, so let's look at what we need to get for vertical load calculations for these brace frames. Again, we're focusing on load combination 5, which I've repeated here. I basically need to get what I'm labeling as VU at the roof and at each of the floor levels. These would be, you could say, these shear forces that are transferred from the floor system or the roof system as concentrated loads to our braced frame columns at each of the levels. Also need to get QU at the roof and QU at the floor. So these are distributed vertical loads that are applied from our roof system and floor system directly to the spandrel beam that's in our braced frames. And then we've got the overall destabilizing effect of all the gravity columns we have in this building. And so if you glance back at the building plans that we had here, we basically have a fairly significant number of gravity columns in between column lines A and F. And so in the east-west direction, we're basically counting on the diaphragms to essentially transfer any destabilizing effect from all those columns and essentially brace those columns, tie them back to the lateral load-resisting systems, our moment frames. And in north-south direction, same sort of deal, but the diaphragms basically providing support to each of the, for all the columns between column lines 1 and 8, as well as a few columns on column lines 1 and 8, tying everything back to these brace frames. So that's our key thing here. So right now we're looking at the design of these brace frames, so we're focusing kind of on north-south effects here in our building. Now, I couldn't figure out a better name to use for dummy column loads than dummy U here. So dummy U at the roof and dummy U at the floor. We need to basically get the total of all the destabilizing load that's not applied directly to our brace frames, and we're going to apply those additional loads to get the total destabilizing effect on our brace frames to the dummy columns. You can see I've got a pin shown at each of the kind of above and below at each of the levels on the dummy columns. So the dummy columns are not providing any restraint of lateral movement. And then I have a strut that's pinned and tied back to the brace frame, so that's allowing us to get our influence of the overall destabilizing effects from all the other framing in the building on our brace frames. Okay, so load takedowns. We've got roof loads. We walk through everything. We're basically a 3.5-foot tributary width on the spandrels for the dead load. 9.25 foot of facade that's supported at the roof level. Same 3.5 foot again. We're looking at snow plus rain on snow. And so we do our total dead load combination with load factors 1.23 on dead load, 0.2 on snow load. We get 443 pounds per linear foot. Keeping up with that at the floor level, tributary width on the spandrels is 5 foot inside. Again, the 0.5 foot overhang outside the exterior column lines. The facade load, 30 pounds per square foot on 13.5 foot height. Then we've got 100 pounds per square foot in the floor area at the stairs, in the bays that basically have the stairs, 80 pounds per square foot in the office areas. And so we total everything up there for our Q sub U. 1.331 at the stairs, which is the bays that where we have our braced frames, and 1.277 at the office areas that are going to dump some concentrated load onto our columns. So let's get those loads. We're going to focus on column D8 here, and as being a representative column load takedown here. From our roof, we're basically going to get a load that is the 1.23 times 22 PSF, 0.2 times 8.5 PSF, dead in snow. You can see below, I've got a 24-foot width, actually a tributary width that's coming in for D8 of 24/2 or 12 feet. The other dimension of that red shaded tributary width is 37.5 feet. So if we tally up our load from the roof, the factored load that we're coming in as concentrated load from that tributary area here is 12.9 feet. At the floors, it's similar. We've got the dead load, 82 PSF, 82.5 PSF, times 37.5 feet times 20 foot over 2, and then 80 PSF on the office areas outside of the central bay of the building, 100 PSF on the area inside, and so basically the red shaded area that you see on the right at the floor levels, we take all that tributary load, dumping it as a concentrated load on the column, 54.6 kips. Coming from the spandrels, we've got tributary load with the spandrel load we calculated earlier at the roof, 443 pounds per linear foot, times half of the span length of the spandrels here between column lines E and D, 22.5 foot over 2. It gives 5 kips. And then a similar calculation at the floor levels, 14.4 kips. If we tally all those up, we're basically going to have a concentrated loads we're going to bring into our column of 17.9 kip at the roof, 69.0 kips at the floors. All right, so in terms of getting our overall destabilizing effects on the building, we need to total everything up in terms of what's that total load that tends to destabilize our braced frames at the roof. And so our basic dead load allowance on the top, the dead load of the mechanical area, the 90 foot by 30 foot mechanical area, weight of the screen walls around the mechanical area, our 60 PSF roof mechanical equipment, the exterior walls supported at the roof level, and all that totals up to 959. Then at the floors, our 82.5 PSF dead load allowance at the floors, then our 30 PSF again on the exterior walls, 13.5 foot of exterior walls supported at each floor. So that gives us 2,376 kips for each floor as total dead loads that's needs to be stabilized by our lateral load resisting systems. Looking at snow load, uniform snow plus rain on snow at the roof, 8.5 PSF times the overall roof area of the building, 211 by 121, gives us 217 kips at the roof. And then floor live load, 80 pounds per square foot on the office areas, 100 PSF at our our bay containing the stairs, 125 foot on the 150 foot by 30 foot area in the middle of the building that we're assuming is designed for storage. And so we get a total at each floor of 2,281 kips. All right, so we're almost there with all these load tallies. If we look at the total factored vertical load that we need to stabilize by our lateral systems, then that would be our 1.23 times 959 plus 0.2 times the snow load at the roof, 1223. Each floor, 1.23 times the 2376 plus 0.5 times 2281, so 4,063 at each floor. And as I said earlier, we're going to focus on the total vertical load supported by the bottom story, or we're going to focus on design of the bottom story members in our brace frame. And so if we tally this up, total load for the whole building, 1223 plus 3 times 4063. So we've got 2 braced frames to stabilize our total vertical loads. So we take half of that, gives us 6,706 kips that we need to stabilize by each braced frame. So that's our piece story here for our braced frame design. All right, so back to the dummy columns. Basically, any load that's not applied directly to our building, to our brace frames, needs to be handled by the dummy column. And so we've got our 1223 kips over 2, but then we subtract off the directly applied distributed load at the roof of 0.443 kips per linear foot over 30 feet. We also subtract off the concentrated load applied to our brace frame columns at the roof. So that gives us a total of 562 kips per braced frame at the roof. And then also at each floor level, we would take the total load that is being stabilized by the brace frame, 4063 over 2. Again, minus 1.331 is our distributed load on the spandrels of our brace frame, 30 foot long. And then we've got 2 69 kip loads that are concentrated loads applied directly to the columns at each floor level in our braced frame. And so the total dummy column load that we need to handle all the rest of the gravity loads that we're stabilizing by each of the brace frames, 1,854 kips. All right, so if we put all that together and summarize it, then here's the sketch that basically shows all of those loads. We're now ready to try to do something with them. How do we now handle the stability design for these braced frames and accounting for these load effects? So a big emphasis here that I'm trying to get at here in this presentation is how we can use our surface wind drifts, our seismic drifts, our seismic P delta limits to come up with a reasonable upper bound side sway amplifier. And what you're going to see is that it's not huge, but it's measurable for the bottom story in these brace frames of our building. So let's get started with looking at, let's suppose that we're going to design this building with a LN500 surface wind drift limit at each story, first order. Now we're going to talk about how we could do a second order. We could look at an actual second order wind drift, which is what we may want to do if we're focusing on a rigorous damage criterion, and what we might use with that typical drift limit. If we're doing that, might be LN400. But we're going to get into that with the moment frame in this building. And so here I want to just assume that we're going to do a first order wind drift of L over 500. The wind load that we would consider, of course that's generally up to the engineer and the client, but a typical wind load level that would be reasonable to assume would be the wind load associated with a 10-year mean recurrence interval. And if you look in ASE 7 for what that is compared to the nominal load, it's only 44% of the nominal wind load that we would use for the strength design. So quite a bit lower than what we would use for strength design. It would be very conservative to use the strength design load in order to look at the service wind drift limit in general. So let's go with that. We had 147.2 as the story shear in the bottom story level under wind that I had shown you earlier. So we'll take 44% of that. We divide by 1 in 500 as our drift ratio that we want to allow for first order. And so if we're going to get that, we're going to have a story stiffness, a minimum story stiffness of 32,400 kips per radian here in our bottom story. That's one number now that we can look at, that we're going to need at least that much in terms of story stiffness to meet this wind drift limit I've just thrown out. Okay, well, what about the seismic drift limit that would come from ASCE 7, sections in ASCE 7 corresponding to that I'm showing you here. And so that seismic drift limit for this particular building design would be basically L over 40, story height over 40. Our C sub D factor for the seismic design here is 3, though. And so if we're really talking about what's the elastic drift given the seismic story shear I'm calling H sub E here, then that drift ratio is 1/3 of 1 in 40. That's 1 over 120. That'd be our elastic drift ratio under the seismic story shear H sub E. And so if we work with that, the seismic drift limit for this particular example would then be 240.2 divided by 1 over 120. So we need at least 28,800 kips per radian. Okay, well, so far the wind drift limit would be the larger one. We'd have to go with that. How about seismic P delta? Well, here I'm showing you the seismic P delta equation from ASCE 7, section 12.8.7. We can basically simplify this theta equation here, basically our stability coefficient, down to P sub x that we'll define on the next page, divided by a PL story minimum. Basically, once we consider that delta over C sub D, it's basically taking us back to an elastic limit here that'd be delta H sub E. We need to keep that less than a theta max, which would be 0.5 over beta over C sub D, but not greater than 0.25. Given that C sub D is equal to 3, we put that in. For a brace frame design, I think it's reasonable to just go with a beta of 1. The brace frames are typically going to be governed by strength anyway. And in fact, if we look back on the previous slide where I was showing you a wind calculation, a lot of times there I might say, oh, okay, I think actually probably based on my experience, my brace frames are going to be even stiffer than that wind drift limit. So I might go with an LN 700 or something like that, or whatever I could guesstimate. Where I think my brace frames are going to be in terms of the drift ratio under my service wind loads. Here with the seismic P delta limit, if we go with C sub D of 3, beta of 1, it means theta max is going to be 0.167. And so if we equate that to P sub x over PL story minimum, solve for PL story minimum, our minimum PL story is 6 times P sub x. Now P sub x is basically defined as the total vertical design load in ASCE 7. ASCE 7 section 12.8.7 says that when we compute P sub x, we shouldn't take any individual load factor exceeding 1. Common practice is using 1.0 dead plus 0.5 live, 0 snow in Atlanta, where snow is less or equal to 30, design snow is less than 30 PSF. And so at our bottom story level here, we basically have our P sub x is our vertical load supported per frame at the bottom story level. And so if we tally everything up, we've got 5754 kips. All right, so if we put that back in, 6 times 5754 is 34,520 kips per radian. And so that's the one that's going to govern here. Our seismic P delta limit is controlling or governing our story stiffness here for our frame. So to summarize here, in terms of now, given our story stiffness, we can calculate an upper bound estimate of our sideway amplifier. Looking back at the equations from Appendix 8 in AISC that we've been talking about earlier, since there aren't any moment frames in the north-south direction, R sub m would be 1.0. There are no moment frames, so hey, it's just 1. PE story minimum, that would be R sub m times the PL story, so equal to PL story. The PL story that we tallied up earlier, 6,706 from slide 43. And so given what we've got here, we'd say, okay, when we're designing these braced frames and we're looking at the bottom story level, we should be using a sideway amplifier of 1.24 as essentially an upper bound estimate. If basically our brace frames just come in just barely meeting our seismic P delta limit, then the actual value would be 1.24. Now, typically for brace frames, they're going to be governed by strength, though, so this is going to be a little conservative. All right, well, we could stop there and run with it, but I want to show you some things with live load reduction next. Basically, the issue is that do we really need to assume that we had this building packed to the gills with live load to come up with our second order amplification? So we'll pick up with that in a minute, but Brent, I think this is my stopping point if there's any questions that I could handle here.
Okay, Don, let's do a couple of questions before we move on. The first question, can you clarify with the dummy columns? Are dummy columns the same thing as leaning columns?
Okay, good question. Yes, or another name we often are throwing around here is gravity columns. So we're basically assuming that leaning columns and gravity columns and dummy columns, they for purposes of our analysis idealization, they do not provide any contribution to lateral load resistance.
Okay. Can you go to slide 29 for me, please?
Okay.
Okay, the question is this. I'm looking at the second line there that shows 0.25 live in storage areas. The question is, how does the 0.25 live relate to the 0.5 L in ASCE load combination 5? And you can find the load combination on slide 34.
Yeah, we're good. Okay, so here we're just looking at the effective seismic weight. And so I'm working from the ASCE 7 here. Probably should have given you the ASCE 7 section. Not sure I can look that up on the fly here. It's in Chapter 12 of ASCE 7. But I'm basically just working on the effective seismic weight calculation here. And so this is separate from the load calculations that we're doing to basically get the earthquake load combination.
Okay. Can you go to slide 47, please?
Okay, and effective seismic weight is section 12.7.2 of ASCE 7. Which slide?
I'm sorry, Don. Can you repeat that section again?
Section 12.7.2 basically gives you the ASCE 7 requirements for your effective seismic weight.
Okay. And then can you go to slide 47, please? And we just had a couple questions on P sub X, so I'd like you to review this once again. One is, I guess, just a quick overview again, once again, what P sub x is, and if there's a reference to where, if there's an equation reference for that specific
right.
variable.
Okay. Yeah. All right. So let's see. So P sub x is basically defined here on slide 48, and I'm referring you to section 12.8.7 for P sub x. And so the definitions that are the common practice here for P sub x, we would basically take the dead load, 0.5 the live load, and if the snow load is less than 30 psf, we don't take any snow load for this.
Okay. All right. Why don't we go on? So let's move up to 51.
All right. Okay, so let's talk about a kind of a neat live load reduction procedure. I think this may have been one of Ron's first papers with Professor McGuire in 1992. And basically, what the procedure I'm going to lay out here is essentially accomplishing the same things that Ron and Professor McGuire were using here in their paper. The calculations are a little bit different than what they're showing in this engineering journal paper from '92. So we're going to first determine all our factor reducible live loads that are applied to the brace frames and their dummy columns. Now, in our frame here, the live loads between column lines C and D aren't reducible, and so they're not included in our calculations. And so that's the gray shaded areas here that we're basically not including in the live load reduction calculations. And so we're working on 0.5 live load in our ASC load combination 5 for earthquake here. And so I tally up 9.0 kips that's transferred from the east-west girders on column lines C and D from the 80 PSF that are outside of column lines C and D. The spandrels outside of column lines C and D, basically those 22.5 foot long spandrels, we're collecting 2.5 kips of for 0.5 live from those. And so a total of 11.5 kips. Now we need also the 0.5 live on the dummy columns. So 0.5 times our 80 PSF times 2 areas, 45.5 foot wide in the north-south direction, 211 foot long in the building, multiplied by a half since there's 2 north-south brace frames. Then we need to subtract off the 2 brace frame columns times, call it VU, or the times the 0.5 VL that I'm showing you above, 2 times 11.5. And I'll leave that out as 384 minus 23 at each floor for purposes that you'll see here in a minute. And so here's a summary of all that showing these factored reducible live loads that are applied to the brace frame and its dummy column. All right, so once we've done that calculation here, we'll basically do a live load takedown in our columns, just tally everything up as we go down the building. What's the axial force supported by each of the members. Now let's get our influence areas for each of the columns. And again, the areas that don't contain reducible live loads aren't included in the influence area. And so if we're looking at the 3rd story columns, from that floor, we basically have 30 foot by 45 foot plus 0.5 times 22.5 as influence area on the brace frame columns. 2 times that for the 2nd story, 3 times that for the 1st story. If we look at the full 3rd story, which is basically what I'm considering as influence area when we look at the dummy columns, so 2 times 211 by 45 feet, and then is the influence area on all the dummy columns, and then 2 times that for the 2nd story, 3 times that for the 1st story. Now here's the influence area that's basically for the column D8. The gray shaded is not reducible, so I'm not taking that part as part of the influence area. So we have the 30 foot by 45 foot here, and then plus a half foot times 22.5. coming into column D8 as influence area. So formal definition of influence area here, if I put a point load at some point in any of this red shaded area, part of that load gets back to D8. So that's definition of influence area. ASCE 7 has factors that try to relate influence area to tributary area, but things kind of fall apart when we get to a more general influence area case. So what I'm using here is a more general definition of influence area to get things. All right, so this slide shows our tally up of the influence areas on each of the columns. Then given the influence areas, we can use the live load reduction equation from ASCE 7. It needs to be greater than or equal to 0.5 for members supporting one story, greater than or equal to 0.4 for members supporting multiple stories. And so plugging into that equation, we get the values you see here on this slide for our brace frame columns and for the dummy columns. So now here's those same factors that are summarized and shown on each of the members of our brace frame and the dummy columns for our structural analysis. Now to move forward, let's calculate 1 minus that live load reduction factor. So we'll show that here on each of the columns. And once we have the that value, let's multiply that by the live load force we had in each member that we had earlier. And so, for example, here we're going to have 0.44 times 23 kips as the example over on the left in the second story column, or in the dummy column, 0.6 times 768. But then we'll subtract off of that. Here's why I kept that separate. I've got 10.1 that I'm subtracting off of the columns in the brace frame, so I'm taking off 2 times 10.1 from the dummy column here. All right, once we've got those internal forces or axial loads in each of the members, we calculate an upward vertical load to be applied at the frame joints to produce the member internal axial force reductions that we just determined in step 6. Now these are loads that we could put into our structural analysis as applied loads that will accomplish the live load reduction that we wanted. Now let's add those loads in, these upward vertical loads we've just calculated to the load combination we already had. And so, for example, there in the at the 4th story level, we had a load of 69 concentrated load coming in to the column, but now we've just figured that we can subtract 3.9 at that level. Down at the 1st floor level, we had 1854. We can subtract 214 kips. All right, so basically that's giving us the live load reduction effect. Why go through all this? Well, actually the common procedure is one where we would apply the full unreduced live load to the structure. We would perform our global structural analysis based on this unreduced live load. We determine the unreduced internal axial force in the columns from the full applied live loads, and then as the last step before we go to the member design, we of course then apply our live load reduction factors. What I've just shown you accomplishes basically gives you the same reduced live load forces in the members, but we are performing the calculations in a way that reduces the applied live load forces in the global analysis, and by doing so, the global second order effects are going to be reduced. That basically our customary approach analyzes the structure filled to the gills with unreduced live load, and so we tend to produce what you could say is an unjustified larger second order effect. All right, so let's see what we get for our brace frames here in this case. If we go through our design here, but we reduce things based on what we just had. So basically our P story at the bottom level gets reduced by 691 kips, looking at the numbers we just calculated. takes our P-story down to 6,015 kips. And so we got a reduction of from 1.24 to 1.21. Not all that much here for the brace frames, but it's measurable. Now, in a case if you have a building that has a particularly larger side sway amplification that you may have sometimes for moment frames, then it can be very beneficial to use this procedure to get yourself a little bit of a break in terms of what we would design our structure for in terms of overall side sway amplification effect. All right, well, let's take that and run with it. Let's design our bottom story column. And so using the equations in Appendix 8 of the AISC specification, we're basically designing our brace frame as a vertically cantilevered truss system here. So we're neglecting second-order or secondary moments in the members of our brace frame, just designing them for axial force. The calculation then is axial force of PNT plus B2 PLT. Now, I'm actually using the procedure I showed in the earlier lecture that gets you into trouble if you have a frame that has significant side sway under gravity load, but everything is symmetric here. So this procedure is basically I'm going to use my gravity force plus B2 times my force in the member from lateral load calculations. And when we do that, we basically end up with 261.1 plus 1.21 times 186, so 46 kips. If we look at our KLX, KLY, and KLZ, that's 13.5 feet. And so Table 4-1, AISC manual, we could use a W10 by 54, 12 by 53, or 14 by 61. Let's go with a 12 by 53. So PCPN from Table 4.1 is 514 kips. If we go to the diagonal brace design, very similar here. For the diagonal, I'm going to size a diagonal here in HSS, square HSS section. And so here from Table 4-4, an HSS section of 9 by 9 by 1/4. Okay, let's keep rolling from here, and then we'll, when we get a little bit further in terms of looking at some things with the B2 estimate, we'll look at some further questions if there are any with the moment frames. So here for the moment frames, very similar vertical load takedowns to what we did with the brace frames. We're going to back calculate a first order serviced wind drift limit necessary to satisfy an actual second order limit. That actually comes from Bill LeMeasure's work. He first published that in '77 in the ISC Engineering Journal. It's kind of a very neat little calculation. That's kind of the major emphasis here. We'll then tie that in with upper bound estimates of B2, and we'll talk about characteristics and kind of generalization of what we're seeing with those calculations. We'll wrap up with strength design and then look at story stiffness design here. All right, so this is a similar graphic to what I showed you with the brace frames. For my preliminary design here, although we have secondary members or infill framing in would put concentrated loads on our spandrels. Here in our moment frames for preliminary design, I'm going to design the spandrels taking all those loads as an equivalent distributed load of Q sub U at the roof and at the floor levels. We also have a V sub U at the roof and the floor levels that's coming in at the end columns, and we need to get a dummy load from our columns at the roof and the floor level, similar to what we did earlier for the brace frames. And so I want to step through this. It's kind of more of the same here in terms of how we're handling things at the roof. At the floors, our Spandrel distributed loads. So here the tributary width is 45 foot over 2 plus 0.5 foot outside the column lines. If we combine all that in with our facade loadings on the spandrels. We get at the roof 1 kip per linear foot. We get at the floor level 3.75 kips per linear foot. If we look at the concentrated loads on the ends, they're loads coming from a 22.5 foot long spandrel. Those loads happen to be exactly the same loads that we calculated on column D8 earlier. And so you can look back for pretty much just repeating those calculations. Now, being a little bit anal retentive here with the slab load on a 1/2 foot by 1/2 foot piece outside the columns, as well as the cladding load pretty much there at the corners of the building for VU2. So if we add all those in, we get 5.7 and 15.4 kips. Total factor vertical load, hey, it's the same as what we did earlier for the brace frames. So we can kind of skip through this. Total bottom story, piece story, 6706 per frame, same as what we had earlier. Now, a little bit different now that we're talking about our moment frames in the east-west direction. We've got a PMF, 1 kips per linear foot times 210 feet at the roof level, plus the 2 5.7 kip loads at the ends of the moment frames, 3 floors times 3.75 kips per linear foot times 210 plus the 215.4 kips at the end columns of our moment frames. So the total vertical load at the bottom story that's supported by our individual moment frames on each frame is 2276. And so we need this to get our R sub M factor that we talked about, 1 minus 0.15 PMF over P story. So we get 0.94, and this accounts for P small delta effects on our moment frames, basically on the side sway drift in our moment frames. All right, factored dummy column loads to get the overall destabilizing effects are 1223/2, same as before, but now minus 1 kip per linear foot times 210, minus our 2 times 5.7 at the roof, so 390. Dummy column load the floor, similarly 1,213. So summarizing all that, we end up with the loads you see here on this particular slide. All right, so now to basically get at the calculation that I want to highlight from Bill LeMeasure's work, we need to look at our total service vertical load stabilized by the lateral load resisting systems. And so for that, we're going to look at our service wind load combination of 1.2 dead plus 0.5 live plus 0.5 snow plus 0.44 wind. And so with this combination at the roof, we basically have a load applied at the roof, 1068. We have at the floors, 3,516, and that's neglecting a small vertical component of wind at the roof that would come from the directional method in ASCE 7. So at the bottom story, if we tally all this up in our service wind load combination, ASCE 7, we have 5,808 kips. And for all practical purposes, the R sub M might change a little bit, but it's going to be roughly about 0.94. So let's go with what we just calculated from load combination 5. All right, so this is the key slide here. The service wind drift limit, if we want to focus on something where we say, hey, I really want to focus on a damage limit under second order drift in our frames here. And so if I'm doing that, when we get our story stiffness design, there we're focused on first order service wind drift. And so we need to convert back from our actual limit on second order drift, and let's go with 1 in 400 as that limit. So that would be, we call psi 2 here. Now psi 2 would be a amplification factor, B2S meaning S meaning for under the service load condition here, is our first order limit at service load over L times that would be we need to compare that to side 2. All right, let's put in the equation for the side sway amplifier. The delta 1 over L, that would be our story shear H sub S divided by PL story. Now let's basically do a little algebra, and so we can get this equation to the form I've just displayed now. If we take that a little bit further, PL story divided by H sub S is 1 over psi 1. And so that's the only change here in going to this form. Now let's solve for psi 1. So psi 1 is the limit on the first order surface wind drift that we would need if we want to ensure that we're not going to exceed whatever our specified value is for psi 2. And so 1 over psi 2 is, or psi 2 is 1 over 400, or 1 over psi 2 is 400. We'll plug in all the other values that I've given you here to this. And so what we've got out of this calculation is to keep the second order drift below 1 in 400, I need to keep my first order drift on my moment frames below 1 in 593. All right, let's use that. So for our wind drift, if that's our limit, if we plug that in, we get 18,970. If we go to our seismic drift limit, similar to what we had before, and so that elastic drift limit is 1 over 120, and so the PL story minimum to satisfy that, 15,230. So far the wind drift limit is going to govern here. Let's look at our seismic P delta. So this is the same as before, except for the moment frames. Typically for moment frames, it's usually a reasonably good assumption for a multi-story moment frame to assume that beta can be less than or equal to 0.67. Basically meaning that the actual lateral load at essentially a first yield condition is going to be less than or equal to 2/3 of the overall lateral load, say in a pushover type of analysis once we get to the lateral load capacity of the frame. And so if we go with that as our assumption, then the theta max on the frame is 0.25. And similar to before, instead of 6 though, we get a 4 times P sub x for our PL story minimum. All right, so now same as what we had for brace frames before, the P sub x, 5754. Let's bring that in. 4 times 5754, 23,020 kips per radian. And so similar to what we had for the brace frames, the seismic P delta limit is governing here for our particular design. Okay, so now we're ready to get an upper bound B2 estimate. I had indicated that we would design the moment frames by direct analysis method. Now the R sub m was 0.94. Our PL story minimum that we just calculated, 23,020. So our PE story minimum, this is basically the only place that our elastic stiffness reduction that we've talked about for the direct analysis method is coming in here. So we have 0.8 times R sub m times PL story minimum, 17,310. Now we're assuming tau of 1. We'll need to check that once we get our column designs, but what we're going to find here for this frame is the column loads are well within the limit of 0.5 py for the P sub u, where so below that we can take tau equals 1. Our P story is 6706 per frame from slide 74. Now this is not accounting for any live load reduction effects. We could do that live load reduction calculation, but in the interest of simplicity here for the moment frames, I'm not showing it. So here in this particular case then, if we put everything together, we've got a B2 max of 1.63. That's less than 1.7, so our frame is not stability critical. If we were greater than 1.7, we would be required to calculate a notional lateral load or an out of plumbness effect and include that in addition to the lateral load from the earthquake. All right, well, let's generalize what we just did here. We need to determine generally required minimum story lateral stiffnesses. So PL story minimum, that can be determined from our service wind limit in the first bullet here, sub-bullet here. The seismic drift limit. Now, if you have a single-story frame, that drift limit can be excluded as long as your walls, etc., in the structure are able to take the larger drifts without damage. And so in a lot of single-story type frames, many times we don't use the seismic drift limit, and that actually allows for the fairly large second-order effects I showed in the earlier example with the direct analysis method for a single-story example. We have 6px for brace frames, typically using beta of 1, 4px for moment frames, assuming a beta of 0.6 less than or equal to 0.67. So PL story min, 0.8 rm times our PL story min. We get our P story from the applicable load combination, and then plug that into B2. So what can we expect? If you kind of walk through our general calculations, you can convince yourself that under wind and earthquake load combinations, then practically for all multi-story buildings, we will always be stability non-critical, B2 less than or equal to 1.7. Now, it's not uncommon for B2 to be greater than 1.7, and therefore for the structure to classify as stability critical under dead plus maximum load combinations in low to medium rise multi-story buildings. So that, but we already require that under gravity only load combinations we include notional load anyway. So it's not really causing us an additional burden, other than the specification disallows the application of effective length method when we have a structure that's stability critical. If we have a case that has load combination 3 governing and large snow load, then B2 can potentially be significantly larger than 1.7 for a lateral load combination here with wind and the maximum snow. Lastly, single-story buildings, as long as we're talking about cases with interior walls, partitions, ceilings, exterior wall systems that are capable of accommodating larger story drifts, those are cases where we could have a side sway amplifier significantly greater than 1.7 if we have large gravity load being taken by the structure. All right, Brent, this may be a good time that we could stop before we kind of look at wrapping up with the member design here. Any questions that we should try to handle?
Yeah, Don, just a couple of quick questions, and then we gotta have a sprint to the end here, I think.
Okay.
On slide 84, the question is, why are we not applying the notional load of 0.002 Y?
Okay, very good question. The reason for that, if you go back to look at what we talked about with the rules for the direct analysis method, basically if it is a stability non-critical frame, then you are not required to include the notional lateral load with a lateral load combination.
Okay. And then I want to jump back real quick to slide 46.
Okay.
Where you look at a maximum allowable first-order service wind drift L over 500 under 0.44 W. Can you clarify where that 0.44 factor is coming from?
Okay. Yeah, if you go to the wind load maps in the back of ASCE 7 for the 10-year mean recurrence interval, And then if you basically do your wind load calculation for those versus the wind load maps for the required strength design wind load, you'll get a ratio of 0.44.
Okay. All right. Let's go back to slide 86 and
okay.
Go from there. Thanks.
Okay. All right. So what I'm showing you here is just a basic preliminary design load calculation next. We'll just kind of wheel through the portal method solution here with the frame. And so given these earthquake lateral loads, we can get our column shears by portal method, our first order column moments, our girder moments, and our girder shear forces, our column axial forces. And so basically working from that, and this for preliminary design, roughing out what we would need for our axial force and moment. Again, similar to what I highlighted earlier, so the PNT in red, the B2 in green, the PLT in blue. And so we get an overall axial load effect on our exterior column here of 254 kips, a little bit of an overturning effect there of 1.63 times 11.5. Now for the MU, question might be, why did you use a B1 of 1? Well, for a side sway moment frame like this, you're never going to get anything other than a B1 of 1. And so once you've done that 500 times, you just put B1 of 1 there. So 1 times MNT plus B2 times MLT, basically doing a conservative estimate of the girder NT moment, assuming that for the exterior column design and designing the bottom story column, basically 1/3 of the gravity moment from the girder is going to be transferred to the column base. And so my rough calculations here then, the B2 times MLT give me a big part of the moment here with this. I need to design my exterior column for 293 foot kips of moment. Now given here, a good place to go is ASE Manual Table 6-1. So here the art to applying Table 6-1 is kind of being able to rough out where do I dive in and try something. I'm going to dive in exactly to the right place here to save time and try a W14 by 68. We've got a KLX, KLY, and KLZ of 13.5 feet. For those lengths, we get a little p-value from the table of 1.52. I'm going to pull my BX naught, which is basically a BX corresponding to a plateau strength for lateral torsional buckling strength of the member, or for length of 0, 2.06. The BX for 13.5 feet is 2.26. And so the B sub X that I need for doing my unity check for my beam column interaction equation will be the maximum of BX for 13.5 feet divided by C sub B and BX naught, the plateau strength. Very commonly for a column design is BX naught that's going to govern. We have a C sub B of 1.75 because of the pin base assumption here in our design. And so we move forward. Little p times PU gives us the axial load ratio. Once we divide that by 1,000, 0.388. That's greater than 0.2, so equation H1-1A governs. And so to complete that out, the 8/9 times mu over phi mn is B sub x times mu, so 2.06 times 293 over 1,000. And so add all those up, we get 0.992, we're less than 1, so we're okay for the column unity check. If we do something similar here for the Spandrel design, so again, we'll neglect axial load in the Spandrel as a typical preliminary design practice. We're going to assume torsion from the exterior walls on the spandrels is resisted largely by the slab and by the infill or secondary beams. And so we'll just focus on our gravity load, 3.75 kips per linear foot on our 30-foot long spandrels. That's squared over 12 as a conservative estimate of the maximum NT moment. B1, 1. B2, 1.63 times my MLT, 178 from the portal method calculations. The unbraced length for this length adjacent to the column where my moment is maximum is 10 feet. And so if we also get our second order shear force at the leeward end of the beam and then move forward with this, we basically get the moment diagram I'm showing you here. I can get a C sub B factor from equation F1-1 in chapter F of the specification of 1.83, and then can go to table 3-2, and we can size our W24 by 62 beam. Basically, what we can view from inspection is that the PMP of 574 should work for this, because LB is 10 feet. That's less than 14.4 feet. And so the phi MR that would correspond to L of 14.4 feet is closer than 1 over 1.83 to phi MP. So if we basically factor up that strength, we know we're going to be on the plateau strength here for the W24 by 62 with this 10-foot unbraced length. And so we're good to go here in terms of the strength we need for this member, 574 being greater than 571. Okay, if we complete that out for design of all the moment frame members, we basically end up with the designs that you see here. I just showed you the examples for the calculation of the W14 by 68 and the W24 by 62. All right, so let's check our story stiffness. Now, a very common procedure for story stiffness would be to use the value of capital G from the side-sway uninhibited alignment chart equations of 10. That factor of G is based on if you had a girder there of basically equal rotations due to side sway at each end of the girder. And so the moments that would come in for those rotations would be 6 EI over L times the theta. And so basically what that means then is to get a stiffness at the base, we can do a 6 EI of the column over L of the column divided by 10. Since G is EI over L of the column divided by EL over L of the girders. Okay, so if we do that here, we get 77,500 inch tips per radian for the W14 by 68 columns. We're going to get, this looks like a typo. The calculations are correct, but I think I ended up doing a copy-paste here on the 77,500. And so I think that's a little bit larger value for the W14 by 90 columns. Notice that there is no 0.8 stiffness reduction here. We're basically going to be looking at service drift. So let's, the simplest thing here is once for preliminary design, now we've got sections, let's get into mass stand in a hurry here and do a calculation to see what we get for our different loadings. So if we look at our seismic drift here under 1.0 of our earthquake load, we're basically well within the 1 over 120 that we talked about earlier, so we're good there. The bottom story, PL story here is 126.9 over divided by 1 over 178 here from these calculations. Now that gives us 22,590. That is slightly smaller than PL story min. And so, and now the PL story min here is basically the one typo that I caught that I'm showing you here, that the actual PL story min that we estimated is 23,020. So we need to increase our story stiffness. How do we do that? What I've found to be a very useful rule of thumb that works in a lot of cases is to basically increase the column sizes if G is much, much less than 1. Increase the girder sizes if G is much greater than 1. Increase both the columns and the girders if we've got G about equal to 1. So if we look at our calculations here that we've got in this case, we have 2.07 for the W14 by 68 columns, 2.86 for the W14 by 9E. And so if we go to the ISOBX tables in Section 3 of the manual, we want to increase the size of the girders. Let's bump our girders up to W24 by 68. Once we do that, we're in good shape. We pretty much are over the limit now, 23,600 being our PL story. We're going to satisfy our P delta, seismic P delta limits. That's bigger than 23,020. We check our wind drift for good measure. We already should suspect, though, that wind drift was not the critical story lateral stiffness requirement. But just to check it out, we end up under our second order service wind drift condition, 1 over 574 for the second order delta over L, which is smaller than 1 over 400. Okay, Brent, I think we're kind of out of time. There's a number of other things that I included as other considerations to limit drift, basically handle composite beam action. So there's some references and some commentary about bringing in composite beam stiffnesses that can be very helpful in some situations. There's also aspects that if you're tight on your drift limits, sometimes you can consider the finite joint size and panel zone deformations. Sometimes that doesn't help you. Kind of as a general rule, using just the infinitesimal size joints and running members joint to joint, the way we've done in our preliminary analysis here, gives us roughly what we get if we actually included the finite joint sizes and the panel zone deformations. There's some references and some points about issues to consider if you go to consider those effects. Then also I had some commentary here, very useful recent paper that's doing a much better job than doing the G of 10 to handle the column base stiffness calculations. Column base stiffness based on G of 10 tends to be rather conservative in terms of estimating what we could get from a nominally simply supported column base in terms of incidental restraint that can help us out on drift and a bottom story. And then lastly, I had given a reference with kind of some illustrations of once you get to more complex systems, it can be very useful to take more of a virtual work-based approach rather than the simple approach I used of just looking at the G factors to figure out whether I needed to increase my column size or my beam size. And so some references to useful material recent work that also provides some good guidance in terms of that. And a lot of the software providers are actually providing very similar capabilities to that. For a basic frame like the one we had, though, I find that just using that very simple rule of thumb I showed you is a very good way to very quickly figure out what do I increase in size, what if I need to increase my story stiffness to satisfy drift. Okay, Brent, sorry I'm a little bit over, but we can stop here and thank everyone for their attendance tonight.
All right, thank you, Don. Great presentation. There's a lot of great information, and as Don mentioned, we were out of time. We did get a handful of questions in tonight, and we do have a few that we did not get to, so we'll work with Dr. White in the Solutions Center to address those. My thanks again for everyone joining us. As always, there's a brief survey at the end. If you would mind, take a moment and fill that out. We greatly appreciate it. And we'll be here next week, same time, same place. Have a good night.